Good morning. Here is me, Teacher Steve, Juma, here to teach you a little bit of maths. The topic today we're going to cover is three-dimensional geometry, that is 3D. And for us to have three-dimensional geometry, then I'm saying it means that there have been a one-dimensional geometry, there have been a two-dimensional geometry, then now three-dimensional geometry. So before I discuss this, let's go back and find out what the one-dimensional geometry meant and what the second dimensional geometry meant. Now to start with, I'm saying a geometric figure, any geometric figure in which only length can be determined is said to be in a one-dimensional geometry. And I'm giving an example here of a line. We assume you're given a line AB. Maybe like I'm showing on my diagram here, on my illustration. Line AB from point A to B, this geometric figure actually. But the only thing that can be determined here is the length or the distance between A and B. Then that simply means that this figure here is in one-dimensional geometry. Then secondly, we also have two-dimensional geometry, and this is a case where a geometric figure in which area can be determined and not volume. A geometric figure in which area can be determined and not volume is said to be in two-dimensional geometry. And I'm very sure you know geometric figures where area can be determined. A good example you can have is a triangle. We can say e.g. a triangle, area of a triangle can be determined half base times height. We have the hero's formula s into the square root of s into s minus a, s minus b, s minus c. Triangle, square, a parallelogram, and we also have a circle. A circle falls under the category of two-dimensional geometry. And that takes us to what we are discussing today, and we're saying that for today we are discussing our number 3, and that is a three-dimensional geometry figures. And we're saying a geometric figure in which volume can be determined is said to be in three-dimensional, let me write this down here, three-dimensional geometry. So when you hear somebody talking about you being in 3D, that means your volume can be determined. But if somebody tells you that you are in one dimension, that is a very big abuse. That the only thing that can be determined from you is the length. Maybe you are tall. Yeah, that is a very big abuse. But when that person tells you again you are in two-dimensional geometry, then that means that person is trying to tell you can only find your area. The area you occupy, the region you occupy, can be determined. And generally anything that has volume should have or should be in three-dimensional geometry. And that brings us to our point of discussion today. And we are saying that today in this topic, what we are supposed to be discussing actually, the relationship between the properties of a solid. And I want to go to another level. These are things you introduced in Form 1 when you were getting the shapes of solids. So to start with this seriously, I would start by saying properties of solids. Actually, properties of solids, when I talk about solids, I know you know them. So the properties, the first ones we have when you're given a particular solid. We have what we call the planes. If not planes, we call them faces. So a solid is defined by the number of faces it has. For instance, when somebody talks about a cuboid, then we see around 6 faces. So before I go there, I've just said that when you're talking about three-dimensional geometry, we are referring to geometric figures in which volume can be determined. And maybe you're wondering, I've not given examples here. The examples here should be cubes, cuboids, a cone, cylinder. All these are solids among others. We even have the sphere. All these are solids whose volume, or geometric figures whose volume can be determined. So when I'm talking about properties of solids, the solids I'm referring to are these: cubes, cuboid, cone, cylinder, sphere, prisms. And there are so many we will discuss as we continue. Frustrums. All those are solids. So these solids have properties that define them, and I'm saying the first category of properties that define solids we have the faces or the planes they have. Number 2, we have what we call vertices or points. They are points on the figures. Another way you would call them, somehow in a very simple way, you would say corners. They are corners of the figures. Then lastly, we also have what we call edges. Edges in the solid, which are actually just but lines on the plane figures. So in this topic, actually, what we are supposed to discuss apart from those ones, we'll go ahead and discuss we call it axis of symmetry. These are some of the properties, axis or line of symmetry. So these are the properties that actually sometimes we say define the solids we are talking about. And I'm saying axis of symmetry gives us what we also call order of symmetry. Order of symmetry. Symmetry, double M. Good. Now, I've just said this topic, the three-dimensional geometry, we are supposed to discuss how these properties are related. And the relationship between these properties takes us to an exercise which I would wish you do. You can try it on your own, find out how many faces are there in a cube. You can go for cuboids and find out how many faces a cuboid has. how many lines, that is the edges, how many points, find out that. A cone, a cylinder, a sphere, these are things you know you did in Form 1. I'll not waste time on that, and even the stories of axis of symmetry and order of symmetry, all these were covered well in Form 2. So today the only thing I want to do is the main thing in this topic, which we are going to discuss, and we're supposed to discuss the properties of solid diamond, the relationship of the faces, edges, and vertices in terms of three things here. And the first one is angle between an edge and a plane. Number 2, angle between a plane and another plane. Number C, we are supposed to learn about skew lines and angles between skew lines. These are the three things in the scope of three-dimensional geometry. So we are saying we're supposed to talk about the relationship between the faces, edges, and vertices in terms of angle between the edge and a plane, angle between a plane and another plane, and lastly, skew lines and the angles between skew lines. Now, to make this so clear, we want to start with the first one. And the first one is about angle between an edge, that is a line, and a plane. What do you do in a case? So we'll start with the first one, and the first case we are saying today is how to determine the angle between a line, and I'm saying a line is the edge, and a plane. This is the only thing you're doing today. We will not rush into it. And I want us to use an example here. Example 1. This is what we are going to use to start with. So I'll quickly write saying determine the angle between VB and the base A, B, C, D in the figure below. In the figure below. And this is the figure. We are not that good in drawing, but we'll try and draw something here that makes sense. One that we can agree with, all of us. So let's assume that is the diagram we have. I'm assuming that that is the diagram we have. not very well drawn, but it shows a picture of what I want. And so we have a center somewhere there. We have our A, B, C, and D. Then we have a V there with the height VO to our center. Oh, so first we are being asked about the angle between the VB and the base ABCD. Before we go there, this is what I would say. A diagonal can be drawn through the center to C, and at the same time from B to D, like I've just done it. So if this is given as 8 centimeters, this is given as 6 centimeters, and that is given as 13 centimeters. We know what we can say about this. Now, to start with, there are steps in determining the angle between a line and a plane. What is the first thing you're supposed to do? Number one, for you to get the angle between a line and a plane, or steps in getting. So step number one, we are saying identify. The first thing is to identify the projection of the line, meaning the edge, on the plane in question. The plane in question. For instance, in this case, what are we supposed to do? We're supposed to identify the projection of what? The projection of line VB on plane ABCD. Plane ABCD. We are supposed to find out what is the projection of VB on which plane? On plane ABCD. Now, the other word I would use maybe to make it clear if you are talking about projection. The projection of a line most probably is a shadow of the line. Shadow of the line. Where will the shadow of the line fall? Now, if we are considering VB, that is line VB, its shadow would only not go past. It will not go past OB. So I'm saying that VB's projection on the plane should be OB. VB. If I'm assuming you're illuminating or you have light from the top, then the shadow of VB would go from B to point O, not beyond point O. So like in this diagram, projection of VB, the projection of VB on plane ABCD is what? Is OB. So the shadow of VB falls on ABCD, but exactly on line OB. That is from the center of the base, that is the rectangle below there, and OB. So we are assuming that this is a right pyramid with the vertical height OV. So from this structure, we are saying the projection of the line is what? OB. Then it simply means after you've gotten this step number one, identifying the projection of the line, the second step should now be step 2. In step 2, we require you to do what we call extract the triangle, extract the triangle that includes the line and its projection on the plane. Extract the triangle that includes the line in question and its projection on the plane. What do I mean? VB is the line we are looking for its angle between it and the plane. So far we have said VB, its projection is OB. There is a triangle you can extract from there. And this triangle, if you are so keen, you'll discover there is something that looks like that. I want to extract it here as we all see. This is B, this is V, and this is O. And for sure, if OV is the height, this is the height. If OV is the height, it simply means this is 90. Remember, this is given. This is given there. We can get it. How do we get it? For us to get the length OB, VB, the VB are the vertical edges, all of them are 13 centimeters. And again, we are saying we can get OB. How would we get OB? The rectangle below there is having an angle there which is 90. That means the length of the diagonals can be gotten. So if we wanted to get DB, we would say it is the same as the square root of the square of 8 plus the square of 6. This is the Pythagoras theorem. And this gives us DB being the square root of 100, which makes DB be equal to plus or minus 10, but for the case of dimension, we remain with 10 centimeters as the length of DB. But since O is the point of intersection of the two diagonals, that means it is the center of the base. And that means if we wanted OB is a half of DB, and makes our OB be how many centimeters? 5 centimeters. So we can also extract that there and say that this is 5 centimeters. After having all this information, you can proceed. If you wanted, you would proceed and say, still with Pythagoras theorem, you will find this to be 12 centimeters. But beyond that, we can go to step number 3 so that we see how to go about this. So step number 3 says what? Our step number 3 now gives us the conclusion. Step number 3 is the conclusion, where we are now saying that the angle between the line and its projection, the angle between the line and its projection on the plane is the angle between the line and the plane. What are we saying in short? If you are able to get the angle between the line and its projection, then it means you have also gotten the angle between that line and the plane that was there, the plane in question. So in this case, the line we have is VB, but the projection is OB. We are asked about the angle between the VB and the plane, but we are being told in step 3 that if we can get the angle between the line and its projection, then that angle is the same as the angle between the line and the plane. 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 So how do you go about this? From the triangle we extracted in step 2, we are discovering that the angle here has a relationship between it 5 centimeters, 13 or 12. We can use any. From SOHCAHTOA, we can easily and quickly say that tan theta equals to 12/5. And this can give us the theta to be tan inverse of 2.4. Are we there? I hope we are all there. And this one will give us an angle which is about 67.38 degrees. But still, we can use sine theta. So you use whatever is easier for you. And for sine theta, that is opposite of a hypotenuse, we can say 12/13. That gives us theta to be sine inverse of 12/13, which still should give us 67.38 degrees. And if that is not enough for you, you can go ahead and say cosine of theta should be the same as the adjacent to the angle, which is 5/13, which still will tell you that theta will be the same as cos inverse of 5/13, and which will still give you theta as 67.38 degrees. And we are saying this angle we have just gotten is the same as the angle between line VB and the plane ABCD. So what are we saying in conclusion? That number one, for you to get an angle between a line and a plane, you should first find out what is the projection of the line on the plane. If you're able to identify the projection of the line on the particular plane in question, then it means you can extract the relationship between the line in question and its projection. And then step number 3 is telling us that the angle between this line and its projection on the plane is actually the angle between the line and the plane. Just to summarize this and to make it even more clear, just a very small example there. Time will not allow me, but I have to put it down. So I would say this is example 2. Example 2, where I would say study the figure below and use it to answer the questions that follow. Questions that follow. And here the questions that follow would be A, determine, not even determine, just state. Let's talk about state the projection of projection of line EB on the plane A, B, C, D. Then number 2, which is the part B of it, we are saying determine the angle between the line EB and the plane A, B, C, D. And this is the figure. This is the figure here. I'll draw it very quickly so that you don't kill us here. So we go, this is it. Again, this is just but a cuboid, so that you don't think of a triangle, a pyramid to be the only one that you will be asked questions to do with. So this is this is A, this is B, this is C, this is D, that is E, F is here, F, this is G, H. This is 8 as usual, this is 6, this is 7 centimeters. And to make this very clear, we are told first to talk about the projection. So to solve this, that is what you'll do first. And again, you'll do that. So there is the meeting point, the point of intersection of the two. After that, you'll also draw another dotted line from E, and I think it comes from there that way. That is the line EB we are talking about. And if it was okay, I would have used another pen so that you see what I'm talking about. But we're talking about the line there. That is the EB in question, so it is an imaginary line within. So the projection of EB, if you are seeing it very clearly there, you would see that the projection of EB is actually DB, where DE is 7, because it is the height. Then DB is actually the diagonal, which if we were to get, I remember me saying DB in the other diagram was gotten by saying 8 squared plus 6 squared gives us DB to be square root of 100. So DB equals to 10 centimeters. So if DB is 10 centimeters and we have the 7, then it means we can extract. And this is the triangle we are actually extracting. This is a triangle we're actually extracting, and the extraction is there. So we have it there. So we are saying the projection of EB is DB. So we have our E there, we have our B here, but the projection is DB. So if we can get the angle between that and that, this is now our theta. If you can get this angle, then you have gotten the angle between EB and ABCD. And how do we get it? We have said DB is now 10, and our height there is 7. If you are keen enough, then it simply means that theta here is related to 7 and 10 in terms of tan theta will be the same as 7 over 10. That means theta equals to tan inverse of 0.7. I want to rest my case there. Find time, get the correct answer to angle theta. Otherwise, we'll stop there. We'll continue from there in our next class. Unless you have a question, that is all for today.